Welcome back, everybody. In today's lecture, we're going to talk about the first derivative test. And in most of this lecture, we're going to be talking about the first derivative and properties of the first derivative. So the first thing I'd like to talk about is called the increasing, decreasing test. And we're going to work our way up to the first derivative test. But first, I need to talk about this test right here. So it's in two parts. So the first part is if f prime of x is greater than 0, so it's positive, on an interval, then f of x, the original graph, is increasing. And I'd say it's increasing on that interval, but that's understood. So if you have a positive first derivative, then the original function was increasing. And we've seen that before in other lecture videos as well, so this is nothing terribly new. And I have the other situation is true as well. So if f prime of x is negative on an interval, then f of x, the original graph, is decreasing on that interval as well. Okay, so let's look at an example where we apply this this idea too. So here's an example. And I'd like to know where, or for what x values, is f of x equal to x to the fourth minus 4x cubed increasing. And then I'll follow that up by saying, how about decreasing? Okay, so let's take a look at this. I'm going to apply this increasing, decreasing test to find the intervals where this original function f of x is increasing and decreasing. So what I need is the first derivative. So your first thought for increasing, decreasing should be first derivative. So the first derivative of this, using my power rule, is going to be 4x cubed minus 12x squared. And I'd like to know where this is positive and negative, so it's going to help me if I set this equal to 0 and then find those values that I need to test around. So let's set this equal to 0. And I'm going to factor this by factoring out 4x squared from both terms. And then this will leave me with x minus 3. So if you find the two x values that make this true, you have one of them at x equals 0. And there's another one here at x equals 3 that would make this 0. So this gives us intervals to test, and we're testing in the first derivative. So let me write that in parentheses. So test in the first derivative, because you want to know whether the first derivative is positive or negative. So let's plug in these values into the first derivative. I'm going to use this one right here. So maybe I could use -1. I could also plug in 1, and I could plug in 4. And I'm just concerned with what the sign of this is going to be when I plug it in. So if you plug in -1, I'll do my work just below here. You get 4 times a positive number, because x squared is positive, so positive. And then -1 minus 3 is minus 4, so it's a negative. So overall, I have 4 times a positive number times a negative number. This is negative. What this lets me know is that we're decreasing for this interval right here. And then if I plugged in 1, you could do the same thing I did before. If I plug in 1, I get a positive, and a negative. So again, overall, I get a negative. So I'm also decreasing on the interval 0 to 3. And then last, I get a change here. So from 3 to infinity, on this interval, I'll plug in 4 to test. If you plug in 4, you get 4. You plug in 4 here, and you always get a positive number for x squared. And then 4 minus 3 is a positive. So finally here, we get a positive, and this means that we're increasing. So now, if I answer the original question, I'll do it down here. You could say we're increasing for the interval 3 to infinity, and then we're going to be decreasing everywhere else. So we're decreasing, and this is going to be from -infinity until 3. So it's just the other part of the interval we didn't get before. Okay, so this means that the original graph is increasing through to 0, and the original graph is decreasing from -infinity to 3. Okay, so now that we've covered this, I'd like to go into what the first derivative test is. So let me switch my color here, and then we're going to talk about the first derivative test. So this is the first derivative test. And here's what it says. So suppose that C is a critical number of a continuous function f of x. Then all of these things are true that I'm about to say. So the first thing is that if f of x, or if f prime of x changes from positive to negative at x equals c, so at the critical number, then f of c is a local max. In this situation, we go from a positive first derivative to a negative. The other side of the coin is true as well. So if you have the derivative, if f of x changes, so f prime of x changes from negative to positive, I should say again at x equals c, then f of c is a local minimum. And then finally, there's a third thing that could happen. If f prime of x does not change sign at x equals c, then there is no local max or min. So you're looking for some kind of sign change to happen in the first derivative with the first derivative test. So earlier, f prime of x was 4x cubed minus 12x squared. So look at what happened here. Where did we have that sign change for the first derivative? Well, at x equals 3, our critical point, where the first derivative was 0, x equals 3 had this change in sign for the first derivative. So let's write that down. At x equals 3, f prime of x changed from, and it was negative to positive. And also know that we have a continuous function here. The function we started with was just a polynomial. It was this one right here. So this is a polynomial, which we know is continuous. So we're in this situation right here where we can apply the first derivative test. So if f prime of x changed from a negative to a positive, then we're in case 2 here. So f of 3 is a local, we'd say this is a local min. The way I like to think about it as I'm doing problems is when I'm doing my first derivative test, I'll come over here and I'll draw the original function on top of this. So like here it's decreasing on this interval, so I'll say it's decreasing, and then when you get to 3, it starts increasing. And if you draw the actual picture of the graph on the first derivative test, you can see what it is. So this is a minimum because we go from a decreasing to an increasing. So 3 has to be a local minimum. Okay, great. So we're going to use these concepts, and we're going to do a few more examples of this shortly. So I'll see you in just a moment. All right, so now we have these 2 final examples to practice the topics we just covered in the previous part of this video. So the first example says find the local max and min of f of x equals x plus 2 sine x on the specific interval 0 to 2 pi. Okay, so to find local maxes and mins, you should first think to do the first derivative. So I'm going to look for f prime of x. Derivative of x is just 1. 2 is a constant, so just ignore it for now. And the derivative of sine x, as we learned in lecture 14, is cosine of x. So here's our first derivative. So we need to find the critical numbers. So there's two situations where that can occur. The first is where the first derivative is 0. So let's try to set the first derivative equal to 0 and see what we get. So this means that 1 plus 2 cosine of x equals 0. If you subtract 1 and divide by 2, that means cosine of x is negative 1/2. There are a couple spots where that can happen on this interval right here. So let me take a moment to draw this out. This is why you've got to be good at your unit circle. So where is cosine first equal to 1/2? Well, that's going to be at pi over 3. So we have pi over 3, and that's where cosine is 1/2. However, I'd like it to be negative. So in which quadrants is the first coordinate negative? And that is in quadrants 2 and 3. So I'm looking actually for these angle measures right here. Well, if you've drawn this now, you can see that this is just another pi over 3 this way. So this is 2 pi over 3. And then the one that's mirrored down here, this is 3 pi over 3, the x-axis here, 180 degrees. So one more would be 4 pi over 3. So these are the two spots where cosine is negative 1/2. Okay, that's great. So then I found two critical numbers. So x equals 2 pi over 3 and x equals 4 pi over 3 are two x values that make the first derivative, first derivative 0. So these are critical numbers. The other case where we can have critical numbers is where we have x values that make f prime of x undefined. So we also need to find those x values that make f prime of x undefined, but are in the domain of f of x. So do we have anything that qualifies for a critical number here? Well, the first derivative is 1 plus 2 cosine of x. That's not undefined anywhere. This is a very nice continuous function for all x. So we don't get any critical numbers from this step right here. So there's no x values that are going to make this undefined. So these are our only two critical numbers. And now what I'd like to do is find which one's a local max and which one's a local min. So I'm going to do the same thing I did before. I'm going to have an interval. I'm going to have 0, 2 pi over 3, 4 pi over 3, and then I'm going to mark this off as 2 pi. Because remember, the only thing I'm considering here is going from 0 to 2 pi, inclusive. And now I need three numbers to test here. So let's go ahead and do our first derivative test using pi over 3. This will be for the first interval. Here I'll use pi. And then finally I'll use 5 pi over 3. That'll be between 4 pi over 3 and 2 pi over 3. And remember, because I'm looking for increasing and decreasing here, I need to plug these into the first derivative. So I'm going to plug them into this right here. So let's plug it into the first derivative, this one. So here I'll get 1 plus 2 cosine of pi over 3. This one is 1 plus 2 cosine of pi. And finally, this one is 1 plus 2 cosine of 5 pi over 3. Okay, what is cosine of pi over 3? Well, I actually have it written right here for us. It's 1/2. So I have 1 plus 2 times 1/2. So this is 1 plus 1 is 2. That's not so important. What I do want to know is that it's positive. So for this interval over here, we have a positive. We're increasing. The original function, this one right here, not this one here, sorry, the blue one, this one here is increasing. Let's test pi now. So if I have pi here, cosine of pi is negative 1. So I get 1 minus 2 is negative 1. So this is negative, and we're decreasing on this interval. And then finally, if I do 5 pi over 3, right here, it's the mirror situation of what's going on over here. So again, we're going to be 1/2 for cosine at 5 pi over 3. So this is also 2, which is positive, and that means that this is increasing. So now let me take a different color and do what I did before. What I like to do, like I said, is to look at what the the first derivative test is telling me increasing and decreasing, and draw the original function over it. So the original function in green is increasing here. It then starts to decrease at this interval, and then it goes to increasing again on this interval. So in green, I've drawn the original function. And now you can very easily spot what's what. This is a local max because it's the peak of something. So x equals 2 pi over 3. We have a local max there. So I should say we have a local max at x equals 2 pi over 3. And then right here I have a valley here, the bottom of this. So I have a local min at x equals 4 pi over 3. And there we go. So those are the 2 points where I have a local max and a local min for this problem. And we use the first derivative test to kind of get us there. Notice the first derivative test was used as well because this goes from a positive to a negative for the first derivative, and this goes from a negative to a positive for the first derivative. Let's take a look at this one as well. So this is just more practice. We have this function. I'm going to find the intervals of increase and decrease and the local max and min. So if I'm looking for increasing and decreasing or local max and min, I'm going to need the first derivative. So that's always my first step. Remember that you can rewrite this as x minus 4x to the 1/2. That's what I'm going to do. And now I'm going to go ahead and take the first derivative. So this is going to be 1 minus, bring the 1/2 down, and I get 2x to the negative 1/2. So this is equal to 1 minus 2 over root x. Remember, for negative powers, you can bring it down like that. And I'm going to rewrite this still. If I put this over 1, I can multiply by root x over root x, and I get a common denominator. So this is going to be root x minus 2 over root x. And I'm going to leave it like that. So now I need to find my critical numbers. These numbers are going to help me break up that number line. They're going to help me find which intervals I'm testing in the first place. So the first one, is it possible for f prime of x to equal 0? Yes. So if this equals 0, which one of these has to equal 0? The numerator, right? 0 over some number is 0. So this means the numerator needs to equal 0 if I'm going to make this first derivative 0. What has to go here then? Well, I get the square root of x equals 2. So x must be 4. So this is the first critical number. Cn will be critical number. It might not be the last, though. So let's go to 2 here. Where is f prime of x undefined? Let's take a look here. Well, it's undefined for a lot of different x values, right? We need x to be at least a positive number or 0, right, for these radical expressions. However, for x equals 0, it's also undefined because you cannot divide by 0 in this expression right here. So this is undefined. So at x equals 0, f prime of x is undefined. And x equals 0 is in the domain of f of x. That's important. So not only do you have to find a value where f prime of x is undefined, but it also had to be a value in the original domain. And what's the domain of the original? The original's domain was x is greater than or equal to 0. So the first function's domain included 0. And then suddenly, when you took the derivative, it no longer includes 0 for the domain. So this is a critical value as well. So we found both of them. It's 0 and 4. So now, just as usual, I'm going to use these numbers, split things up here. I'm going to have 0 and 4. And also, notice I'm not even going to consider this stuff over here because this is not in the domain. All these negative numbers over here were never in the domain of the original in the first place, so we're not going to have a graph there. So we just need to focus from 0 to infinity here. And I just need to pick 2 different values to test. So the first one I'm going to choose is 1. And for this one, I'll choose 5. And we're just concerned with what's happening with the first derivative here. So we're going to do f prime of 1, and we'll look at f prime of 5. So if you look at f prime of x right here, if I plug in a positive 1, I'll get 1 minus 2 over 1. This is a negative number. So this means on this interval, we're decreasing because we got a negative here. And for 5, what happens? If you plug that into the first derivative, you get square root of 5 minus 2 over square root of 5. This is a positive number because square root of 4 is 2. Square root of 5 is a bigger number than 2. Okay, so this is a positive. So this means we're increasing. So we have one local max or min here. So we have what type? Well, if you take your graph, draw over this. So from 0 to 4, we're decreasing. So it looks like this. And then suddenly we're increasing. That didn't show up very well, did it? So let me try this one. You're decreasing. And then on this part, from 4 to infinity, you're increasing again. So if you draw the original graph over there, you can very clearly see that 4 is a local minimum. So we have a local min at x equals 4. If you wanted the actual value of the graph as well, you can go back to the original. So the actual value is, so if I plug in 4 into the original, that would be up here. You get 4 minus, so I'll do the work right over here. You get f of 4 is 4 minus 4 root 4. And then this is 2, so you get negative 4. So the actual minimum on the graph is 4 comma negative 4. That's where the minimum is. And I'll go one step further. I even looked up what the graph looks like. So I'll draw that for us. I'll just right here. So this is what the graph kind of looks like. So at 0, if you plug it in, it's 0. Here you go down to 4. It goes like this, and then it swoops up. And then it goes like that for the rest of its life. So here's the point down here, 4 comma negative 4. OK, and I'd also like to point out, too, that not only is this a local min, but this is also what type of minimum? It's an absolute minimum. This is because on this, for this whole graph's life, on the whole domain from 0 to infinity here, this is the lowest point that's ever achieved on the graph for negative 4. So negative 4 here is a local minimum value as well. So it's local and it's an absolute as well. So it's both of them at the same time. OK, I hope this helped you with the first derivative test and increasing, decreasing. Go ahead and try your lecture quiz. And if you have any questions, just email me. And I'll see you next time. Bye.